Good morning, everyone. So, does anyone have questions from last class? For basically the most part of a chapter of carboxylic acid, you had the quiz. So you probably know what are the important stuff. And I think we ended the class with looking at the infrared spectrum of typical carboxylic acid. So if you look at the common feature of all infrared spectrum of carboxylic acid, obviously you have to look at the infrared features of the COOH groups. So COOH group, the naturally it has a CO component and the OH component. So CO component is clearly showing here, okay, as CO component around 1700. But OH component is a bit tricky because due to the extraordinarily strong hydrogen bonds, typically found in carboxylic acid, the OH stretching frequencies actually become substantially broader, okay, and lower frequency than typical OH stretching of alcohols. First is lower frequency, second is broader. So OH frequency, OH stretching of alcohols, typically we expect somewhere around here, okay, as intense, relatively broad band somewhere around here. That's OH, alcohol OH. But carboxyl OH, due to extremely strong hydrogen bond, this usually appears in the form of hydrogen bonded dimer of carboxylic acid. So I hope you guys recall. Let's say you have a one carboxyl group like this, okay, and then you have the other carboxyl group. Let's say the other carboxyl group like this. Then you have this kind of cyclic form of hydrogen bond, and the net effect is let's say top hydrogen bond really enhance the bottom hydrogen bond, so the both hydrogen bond become stronger because of this dimer form. So if hydrogen bond becomes stronger, its impact on the OH stretching group is substantial, makes OH group more intense and broader. And it's so broad that it actually appears as a intense and a broader peak, typically sit like here. Okay, that will be the carboxyl OH, and that make it in most of the case very difficult to separate from the the SP, just the CH stretching peaks. It could go from the, let's say, SP2CH, SP3CH. Those appear as sharp peak, but the OH stretching appear as very, the broad and intense background. Sometimes difficult to resolve. Okay? So you can have a better feel when you compare the IR of carboxylic acid and the IR of aldehyde. You can see that why both have the carbonyl group, okay, around 1700, but for the aldehyde, the CH stretching peaks, they are cleanly appears. You don't have a broader and intense background below it, okay? But here you do have the broad and intense. You can feel that, okay? So compare these two, you're gonna have a better feeling. What will be the carboxylic acid IR look like? What will be aldehyde ketone? The IR looks like. And the ketone, as you know, I hope you guys know, ketone, this is aldehyde. The ketone don't have these two peaks. These two peaks are characteristic for aldehydes. Okay? This pair of peaks. This pair of peaks, okay, they come from aldehyde CH, okay, a pair. Okay? Ketone doesn't have that pair of peaks. So that's infrared. Any question about infrared? Under the proton and NMR, nothing especially special. Okay, you know I think it's better using this guy as example. I'm gonna give a different example. Let's say, look at this one. This is the proton NMR of butanoic acid. So this compound has 4 types of protons labeled as A, B, C, D. So the most characteristic proton in this carboxylic acid is the carboxyl proton. And the carboxyl proton is extremely deshielded, often appears somewhere, it has a chemical shift value greater than 10. So this is not a surprise to us because chemical shift value is usually correlate with what? Shielding or deshielding, okay? And shielding, deshielding, other than the field effect, usually correlate with electron density, okay? So the carboxyl proton is the most acidic kind of proton which we kind of normally encounter in organic compounds. Most acidic one, that usually is correlated with very low density around that proton. So that's why the chemical shift value of carboxyl proton is the most deshielded proton we have seen so far. Most deshielded, even more deshielded than phenol protons. Phenol protons, if you recall what you read in chapter 6 and 3, it's about like a million times more acidic than alcohol proton. That's why phenol proton generally is more deshielded than alcohol proton. And the carboxylic acid protons is another million times, roughly, okay, more acidic than phenol protons. So it's not a surprise for us to see the chemical shift values beyond the 10, okay, typically. That's the kind of proton we haven't seen before, such acidic, so low electron density proton. The rest of them, you can just, really, you can apply the same principle, explain their chemical shift values. Like, the C, I hope we can see, okay? The carbon C, okay? Not carbon C, this CH2 is the alpha proton. Is the proton next to the carbonyl group, right? Later, we're going to see this term more frequently called alpha proton, the proton next to the carbonyl group, okay? And as we know, the carbonyl group is what kind of group in terms of electronic effect? Carbonyl group electronic effect is what kind of group? Withdrawing or donating? Withdrawing. Okay. So withdrawing basically is to shield the proton on the carbon it direct connect to. So that's why you see this proton is most deshielded. Chemical shift value is highest, other than the carboxyl proton. Okay. So this 2 point something. Okay. That's just like similar to the ketone proton, the counterparts in the ketones, the aldehyde, they are similar. Let's say if you have this, if you have the, I don't see the join here. Okay, forget about it. No, if you have, the aldehyde, if you have aldehyde with a kind of a similar structure, say CH3, CH2, CH2. You have this compound, okay? Butanol. This got butanol, right? 4 carbons. Am I right? Yeah, 4 carbons. Butanol. Okay. So the 3 carbons other than the aldehyde, the carbon, their chemical shift value, they will be similar trend. So this one, okay, you expect 2.x ppm, okay? This one, proton will be 0.9 ppm around, okay? And this one will be 1.x ppm, okay? Similar, because these 2 protons, they are directly bound to the electron withdrawing carbonyl group. So electron withdrawing effect, the strongest, highest chemical shift value. And the proton on the blue carbon, It's farthest away from the carbonyl group. So it's the lowest chemical shift value. And the proton on this carbon is in the middle, 1.6 something. Okay, exact value I'm not asked to memorize, but relatively. Okay. So really nothing special here. Okay. And the carbon 13 NMR of carboxylic acid is kind of the characteristic peak is a carbonyl carbon. And the carbonyl carbon, just like the ketone aldehyde carbon, they are very, very dishielded. But it's not as quite dishielded as ketone aldehyde. Ketone aldehyde, I hope you recall, around 200 ppm, around 200 ppm. But here, the carbonyl carbon is a bit less dishielded because what can be explained by resonance. Yes, very good. Because in carboxyl carbon, you have this the OH group, okay, can donate, okay, electron density to the carbonyl carbon. So therefore, the carbonyl carbon, is somewhat the less dishielded, okay, than what you see in ketone aldehydes. And the mass, really nothing to talk about. So that pretty much ends the chapter 19. We're gonna move to the chapter 20. Does anyone have questions? Not? Okay, let's move to chapter 20. Chapter 20 has a huge number of reactions. But if you can, what is the problem? Okay, there's a huge number of reactions. However, if you can organize those reactions, let's say in logical manner, you will see that all those reactions can be can fit one simple principle. Okay, so and in this chapter we are dealing with carboxylic acid derivatives. And we will first look at what are the carboxylic acid derivatives, okay? And also we're gonna look at a type of reaction called nucleophilic acid substitution reaction. We already seen one such reactions, and this reaction we actually learned 2 times. First time is we learned in chapter 16. We learned the general outcomes of such a reaction. And in chapter 19, we looked into the great details about the mechanism. That reaction is a Fischer acidification reaction. And if you look at the Fischer acidification reaction, say, just using one example, I believe that's the sample reaction we were looking at. So you have a benzoic acid, then you react with say CH3OH, and this reaction generally is catalyzed by acid. So why is the reaction catalyzed by acid? Why acid can we use in base to catalyze this reaction? Yeah, but if you use the base reaction, will it happen or not? Actually, you will see, this reaction will not be happening under the basic condition. Will not. It's a different from aldehyde and ketones because if you on the basic condition, first thing will be happening is this is a carboxylic acid, right? Carboxylic acid is the most acidic class of organic compound. If it's so acidic, if you treat it with base, what will be the first reaction will be happening if you treat it with base? Let's say sodium hydroxide. Immediate reaction is so this reaction will take a proton away. Okay, take a proton away, and this will give you water and carboxylate. Okay, and as we will see very quickly today, once a carboxylic acid becomes carboxylate, okay, it will be stuck there. We are not willing to undergo any reactions, okay, because, and as you're going to see quickly, carboxylate is the most stable form of the carbonyl groups you're ever going to see. Most stable form. Why? We will discuss about it, okay? So you will be also comfortable. I'm not wanting to change anymore, okay? So this reaction must be catalyzed acid because of the carbonyl group can be protoned by the acid. If you use base, you might think, oh, the base could nucleophilic attack the carbonyl, but it will not because first it will have acid-base reaction to get protonated carboxyl group. Okay. So anyway, so this reaction, if you look at the outcome, I'm trying using color code to indicate the carbonyl groups from the carboxylic acid and this OCH3, okay, and then plus the plus water. So and this reaction, what you can see is in the carbonyl compound, you can break you can break up the carbonyl compound into two parts. Okay, so this is the electrophilic part, and we call it this as a name. We call it acyl group. Okay, this is group. Okay, so the other part is OH minus. We can say, oh, this guy is a nucleophilic part. Okay, so what you can see in this reaction is in the carbonyl carbon, the substituent is replaced. Originally, it had OH group attached to it, right? And after the reaction, you have OH3 replacing it. So this reaction is an example called nucleophilic acyl substitution reaction. Okay? Because incoming reagent is a nucleophile. Okay, so this is a nucleophile, and replace a substituent on the acyl group. This is called nucleophilic acyl substitution reaction. Called nucleophilic acyl substitution reaction. So we already seen this, okay? Nucleophilic ACYL substitution reaction, okay? And if you recall the mechanism, we learned in chapter 19. I want to just the refresh, okay? So for this particular reaction, the reaction has two stages, okay? So first stage, stage 1, yes, addition. And the reaction will give you, addition reaction will give you tetrahedral intermediate. So that's first stage, stage 1 addition. And that usually the first stage is slower than second. Usually, I'm not going to make absolute statement, but let's say in this course, you can safely assume all four stages is a slow one. Okay. Then the second stage. Look at, we can look at the outcome. So second stage, what reaction? Yes, elimination. Okay. Stage 2. E1 actually, we can call it, okay? Elimination. Okay. So actually this will be the general pattern of all nucleophilic acid substitution reaction. All of them. Why that's the case is because of you can consider, because the carbonyl group is the strongest double bond we have seen so far, and probably the strongest double bond you will be seeing in this course. There are probably stronger double bonds, probably, but among common double bonds is the strongest double bond. So it has kind of special stability. You can treat carbonyl group as if it is kind of called the junior version of aromaticity. Junior version of aromaticity. In aromatic, doesn't matter nucleophilic aromatic substitution or electrophilic aromatic substitution. Always you have one step break aromaticity, right? Addition, break up aromaticity, and then elimination to restore aromaticity. So the overall driving force, obviously, is the entire compound become more stable. That's overall driving force. But if addition step breaks up aromaticity, we want to restore the stable form. So same thing here. The carbonyl form we can consider a junior version of aromaticity. It has some this particular stable double bond. So after first step breaks the carbonyl group, the molecule will try very hard to restore its relatively stable form of carbonyl group. That's one. That's why it goes to second stage to restore it. Okay. This is a general principle for all the nucleophilic acid substitution reaction. You will be seeing in the chapter 20. Okay. And the one of the if you write in its general form, a nucleophilic acid substitution reaction will be like this: R, let's say Y. Okay. So this fragment, okay, is a leaving group, reasonable good leaving group. Okay. Then if it react with HX, and the X, okay, is a nucleophilic species. Okay, and the reaction will give you, the reaction will give you so this thing is not necessarily have H there. You could have just the X, okay, and then this one will become Y, okay. So the one of the you probably can see that this reaction could go both directions. Could go left to right, also could go right to left, because in both sides of the reaction, you have the leaving group attached to the acyl group, and Lewis space react with it. Okay, so reaction can go either way. So how do we know which direction reaction will be preferred? There's a very simple principle, will be dictate the direction of the reaction. How do you know? What is this principle and how do we apply it? Yeah. Huh? Could you say again?
The Nietzsche principle is go both ways.
Oh, Le Chatillon principle. Le Chatillon principle. That technically yes, but if it's equilibrium, then you will be know how do you know the equilibrium constant is larger than one or smaller than one? That's what I'm trying to say. Yes, technically they can both go to. If the equilibrium constant is not too larger than one or not too smaller than one, then you apply the Chatillon principle. But if the equilibrium constant is, let's say, 10 to the 10th order, the Chatillon principle won't do much. Okay? If 10 to the 10th, let's say, okay? If 100, yes, the Chatillon principle maybe still can do something. But Chatillon principle is most meaningful if the equilibrium constant is not too far away from 1. So that means the reaction doesn't have particular preference on either side. Okay, then the Chatillon principle is most applicable. But if the equilibrium constant is, let's say, is 10 to the minus 10, then obviously equilibrium favors very favor left side, right? Then yes, the Chatillon principle can do something, but not much. So basically, the question first we need to answer whether the k is significantly larger than 1 or significantly smaller than 1 or about 1. Okay? So that is the question we also have to think about the the reactions. All reactions you will be seeing pretty much is like this type of reactions. Okay, or majority of reactions you will see like this type. So how do I know what is the k value? Okay, that's a question we need to answer for many reactions you will see in the chapter 20. Okay, we will see. You don't need to memorize a particular reactions. I will teach you a principle by systematically looking at the components of the two sides. You can relative effortlessly can reach out to the conclusions. Okay. Now let's first look at what are the carboxylic acid derivatives. Okay. So there are 4 class of compounds of carboxylic acid derivatives. Let's say the 4 official members of carboxylic acid derivatives. There are some unofficial members as well. Okay, we're gonna talk about later. But the 4 official members, they are acyl chloride, okay, acid anhydride, ester, and amide. So the acyl chloride and esters, we have seen it earlier. Acyl chloride, we have seen as early as chapter 13, when we look at the Friedel-Crafts, the acylation reaction. And the acid anhydride, we also, for first time met this guy also in chapter 13, but we didn't, use it as extensively as acyl chloride. So if you don't recall it, I'm not gonna blame you, okay? Amide is probably first time. So we should say hi to amides, okay? So the first time meet this guy, okay? But if you look at the common features of those 4 official members of carboxylic acid derivatives, they all share what structure? All share this one. This called ACYL, okay? All have this group, acyl group. Each one of them have this acyl group. Okay? So the difference is, and another common feature is you always have a heteroatom bound to one side of the acyl carbonyl. Always, okay? Have a heteroatom. So in acyl chloride, you have chlorine bound to the the acyl carbonyl carbon. Okay. In acid anhydride ester, you have oxygen bound to the carbonyl carbon, and in amide you have nitrogen. So all of them has a heteroatom bound to it. This actually is important because the heteroatom can make a polar carbon heteroatom bond to carbonyl group. When this in all those carboxylic acid derivatives, you can have a reasonably good leaving group, at least a potentially reasonably good leaving group bound to the carbonyl carbon. So this is in sharp contrast with the aldehyde and ketone. If you see aldehyde and ketone, well,
what are the groups bound to the carbonyl group? In the ketone, you always have a carbon, okay, bound to the carbonyl carbon. So in the aldehyde, you have one side have a carbon bound to it, and the other side they have a hydrogen bound to it. So in both ketone and aldehyde, you will see that on the carbonyl carbon, you don't have any good living group or potentially feasible living group bound to carbonyl carbon. So that is the biggest difference. And this difference actually leads to the fundamental, different reactivity of ketone and aldehyde and the carboxylic acid derivatives. Okay? So what's the biggest difference? Ketone and aldehyde. If you have the nucleophile react with, the carbonyl carbon, you could have addition reaction, right? But you will not have a nucleophilic acid substitution reaction because in order for the nucleophilic acid substitution reaction, as we see here, okay, this X needs to go away, right? Needs to go away means it must be at least potentially a good living group, okay? But here you don't have such a living group, so that's why ketone and aldehyde will never undergo nucleophilic acid substitution reaction because of the lack of good living group. But the carboxylic acid derivatives, they can, because here the living group is a chloride, excellent living group. If you check the chapter 6, organic 1, when we look at the nucleophilic substitution reaction, this is excellent living group. Okay, and in the acid anhydride, this whole thing is a living group. Okay, it's not as good as a chloride. Okay, but still a pretty good living group. And how do we judge the living group quality? Anyone recall? Living group quality? Living group quality is directly associated with what property of the group? Basicity, excellent. So what kind of basicity is good for living group? The low basicity or high basicity good for living group? Low, yes. So now you can see that this living group, when we say living group, we also talk about the electrons also go with it. Okay. This pair of electrons also go with it. This living group. If you look at it, it's gonna be this one. Okay. If you check the basicity, we just learned in chapter 19. The conjugate acid pKa is usually around 5. Okay. So yes, not as good as chloride, but still it's reasonable living group. Okay. So next one is this guy. The living group is alkoxide. Living alkoxide, if you look at the basicity, I hope most of you should know its basicity is similar with the hydroxide ion. Similar, okay? Similar. I'm not saying exactly, they are similar. And then that means the living group quality, they are similar. They are not good living groups. We know they are bad living groups, okay? But they are possible living groups if the conditions are right. Possible living groups. And besides, you have a potential ability to convert this one to a good living group. How do we convert this one to a good living group? Alkoxide and hydroxide, they are better living group, but it's a possible living. But you have a potential to convert good living. Yeah. Very good. Protonated, like this one protonated become ROH, okay, alcohol, and this one protonated become water. So both these two are equally good, excellent living groups. Okay, and then last one is this one, amide. Okay, if amide, okay, and if you don't remember the specificity, I'm not gonna blame you because we don't use this guy very frequently. But in chapter 9 organic one, we did involve some. And its conjugate acid pKa is around 36. So this is far more basic than alkoxide ion. 20 orders of magnitude more basic. So it's very difficult for the amide itself to directly serve as a leaving group. I said alkoxide is already a bad leaving group, but on a certain extent they could serve as a leaving group. But we probably will not see the condition is amide directly serve as a leaving group. So amide, if Y itself cannot directly, normally won't serve as a leaving group, but we still have a way to convert it to a reasonable good leaving group by the same strategy as alkoxide and hydroxide. How do we convert it? We protonate it. Okay? So if in the presence of proper proton donor, we can convert to say H. Then this leaving group is actually not such a bad leaving group because it's a conjugate acid. Let's say this conjugate acid, okay, the pKa is around, okay, 10, okay. Then it's not a terrible leaving group. It's a possible leaving group. So that's, the overall look of the reaction, okay. So, the common feature of not of a reaction, the structure, there's some overview of the structure, unexpected reactivities of carboxylic acid derivatives, okay. And any questions about the structure overview of carboxylic acid derivatives? The carboxylic acid derivatives, we just call them, the CADs, okay? So the CADs, they are usually formed by, the nucleophilic acid substitution reaction. This is a general, the reaction equation, and you can guess, this equation can convert one carboxylic acid derivative to another by using a nucleophile to react with, the carboxylic acid derivative. So whether this conversion, okay, one key topic in this chapter is what is how about the thermodynamic feasibility of this reaction, the equilibrium constant, okay? So basically, there's three possibilities. K is much larger than 1, that means thermodynamically favorable from left to right. K is much smaller 1, means not thermodynamically feasible from left to right. Or K is about 1. Say, okay, the reaction can go either way. There's no clear preference. Okay? So we will learn, how do we, determine the thermodynamic feasibility for given such reactions, and by using a systematic manner. Okay. So nomenclature, again, I'm not going to really cover it, but not saying not required. Okay. I will test slightly, but you guys can read by yourself. It's just set of rules. Okay. So now directly jump to the structure and the reactivities of a carboxylic acid derivatives. Okay. So as I already mentioned in the couple minutes earlier, all the carboxylic acid derivatives have a potential leaving group with a heteroatom bound to the carbonyl carbon. So the key structural feature that separates the reactivity of those carboxylic acid derivatives, separate those carboxylic acid derivatives, is the ability of the heteroatom in the carboxylic acid derivative to stabilize the carbonyl group. So whatever the heteroatom does, okay, it will impact the carbonyl stability. So if you recall what we learned in chapter 18, in general, how does the stability of a carbonyl group impact its reactivity in general trend? If a carbonyl group is more stable, its reactivity will be lower, right? In general, okay? Yeah, that could be exception, but in general, the more stable the carbonyl is, the less willing to react. Okay? So the same trend applies to here. Okay? So the we basically, I hope in this section, you will develop a clear picture how does the nature of heteroatom impact its, the carbonyl stability. Okay? So overall is the better the heteroatom can stabilize the carbonyl, the more stable carbonyl is, then less reactive the carbonyl is. So that's the, let's see, logical, just mean the way of thinking of this problem logically. First, the better the heteroatom can stabilize carbonyl, okay, then the immediate outcome, the carbonyl is more stable, okay. If the carbonyl is more stable, then the carbonyl is less reactive. Is that very logical? So if the heteroatom can stabilize carbonyl better, then the carbonyl is more stable. Then carbonyl is more stable, the less reactive carbonyl is. Okay. So the overall trend of reactivity is acyl chloride is least reactive, followed by anhydride, then ester, then amides. Okay. So we will see. First, let's look at some, some facts. Okay. The facts is that this guy is most reactive. Okay. This one is least reactive. And then if you look at carbonyl stability, the bottom one is most stable, has most stable carbonyl. And the top one has the least stable carbonyl. And we actually we will at the end of this chapter, we will have some spectroscopy evidence to back up this. Not only, the reaction rate, the data, also spectroscopy features. Okay. So then if you look at the structures of those carboxylic acid derivatives, okay, so the main structure features that distinguish acyl chloride, anhydride, and ester and amide is the interaction of the the heteroatom with the carbonyl group. Okay, so then if you look at such the electronic interactions, you can analyze by using those 3 resonance forms. Okay. So you can look at those 3 resonance forms in the first look at those 3 resonance forms in terms of their contribution to the real structure. So which one makes the greatest contribution out of 3 by just applying the resonance form, the stability you learn from organic 1. So yes, Andrew? The greatest contribution, right? First one, yeah, first one makes a great contribution. See, look at if you look at the resonance form stability, first thing we look at is how many bonds we have. And if you look at that aspect, the central one has 1 fewer bond than the other 2. Okay, so the central one is the least important in terms of contribution. Okay, but if you look at that aspect, the first one and the third one, they are the same number of bonds. Then after number of bonds, then you're looking at the number of atoms with non-zero formal charge. The fewer, the better. Okay, so the first one has 0 atom with non-zero formal charge, so it's best. Okay, so first one is most important, but the third one is more important than second one. Okay, so what you can see is if you look at the third form, the third form reflects that the heteroatom, given its lone pair to the carbonyl group, that's the third form pretty much represent, right? The third form represent where the heteroatom, given its lone pair to the carbonyl group. So you can consider third form represent the characteristic of stabilized carbonyl group. See, once the carbonyl group receives the lone pair, right, the carbonyl group become less electron deficient. Okay? Just logically think, carbonyl group is electron hungry, so if you have a nucleophile to react with a carbonyl group, if you have a nucleophile react with carbonyl group, let's say, whatever nucleophile it is, it must serve as a, what happened? Must serve as a Lewis space to attack carbonyl carbon. Okay? So how fast the nucleophile attack carbonyl carbon depends on electrophilicity of carbonyl carbon. And the electrophilicity of carbonyl carbon is dictated by the charge, amount of charge. Okay? So if the carbonyl group receives the lone pair from the heteroatom, the carbonyl carbon will be less electrophilic. Right? Does it make sense? If it receives the lone pair, then it's less electron-hungry, not that willing to react with nucleophile. Okay, then next thing you can next step. So assume you take this as granted. Okay, well, after carbonyl receives the lone pair, is stabilized, become less willing to react. Okay, and this is the form represent such a characteristic. Right? This form will already show you, the heteroatom give its lone pair to carbonyl. So the contribution of this form, you can directly represent how stable the carbonyl is stabilized, how much carbonyl could be stabilized. So the more contribution this form makes, okay, the more contribution this form makes, the carbonyl group is better stabilized. Because in this form, carbonyl group receives the lone pair from heteroatom. So the more contribution this form makes, then the carbonyl group is better stabilized because it already received the lone pair, become less electrophilic, less willing to react with nucleophile. Any question about this line of thought? Any question about this line of thought? So basically, what we're looking at, for all the carboxylic acid derivatives, okay, qualitatively, how much contribution this form makes, okay, how much contribution this form makes. So if in a carboxylic acid derivative, this form makes very little contribution, that means the carbonyl group in this carboxylic acid derivative is stabilized to a least extent. That will be most reactive. And the question about this way of thinking of this, the stability of carbonyl group in carboxylic acid derivatives. Any question about this way of thinking? So essentially, we are looking at the contribution of this resonance form. The greater contribution this form makes, the carboxylic acid carbonyl is better stabilized, more stable, less reactive. Okay? And then, how do we qualitatively assess how much contribution this form makes? So obviously, if you look at it, in this form, the lone pair from heteroatom is given to the carbonyl group. Is given to carbonyl group. So the willingness of this lone pair to give out, the willingness of this heteroatom to give out its lone pair obviously relate with its electron activity, right? Because after all, from these two guys to here, the lone pair originally belonged to the heteroatom, now become given to the carbonyl group, right? So the electron activity of X will impact the willingness of the heteroatom. The electron activity of the heteroatom, X, heteroatom, will impact its willingness to give out a lone pair. So how does the electron activity impact the heteroatom's willingness to give out a lone pair? If a more electron active element is more willing to give out a lone pair, or less electron active, less so. Okay, so that's one thing to think about. So if the two heteroatoms, okay, in the same period, okay, you will see why I'm gonna mention same period. Okay, if two hero atoms in the same period, okay, the electronegativity will be determining factor in terms of how well the hero atom give out a lone pair. Because the more electronegative element will be less willing to give out a lone pair. And the more less electronegative will be more willing to give out a lone pair. Less electronegative, more willing to give out a lone pair. Like if you, the typical example is, look at these two guys, okay? One is nitrogen lone pair, one is oxygen lone pair. They are in the same period, right? Both second period elements. And as we know, all of you should know, without using periodic table, oxygen is a sizably more electronegative than nitrogen. Therefore, oxygen will be less willing to give out its lone pair to the carbonyl than nitrogen. Okay, so this nitrogen can stabilize carbonyl better than oxygen does because of its less electronegative. So that makes this one carbonyl is more stable than this carbonyl. Therefore, this one is less reactive than this one. That's the electronegativity impact. Okay. The second one, okay, because look at it, in this resonance form, you have a double bond between the hydrogen atom and carbon, right? And the double bond, as we know, always include a sigma bond and a pi bond, right? And then you know the how strong, okay, this hydrogen atom carbon double bond can form also play a very important role. Okay, why? Because as we know, if we compare two chemical bonds of the same bond level, say both double bonds, okay, or both single bonds, we know what is the most important factor affect the bond strength if both are double bonds or both single bonds. From general chemistry, if let's say compare two single bonds or two double bonds, what is the most important quantity that dictates the bond strength? The size, okay, the length, right? The length, okay. So if you are comparing carbon hydrogen atom double bonds, right? The shorter the double bond is, the stronger the double bond is. Okay. If the double bond is stronger, that means this form gonna be more stable. Okay. So that lead to the important factor. The smaller the axis is, okay, it will give you more stable this resonance form. Because smaller the axis, this double bond will be shorter. Shorter will be more will be stronger. If double bond is stronger, then this form will be makes greater contribution. So if you look at just to give you a few examples, if you look at this. So if you look at these two guys, okay, the acyl fluoride and acyl chloride, okay, it actually is a fluoride, okay. The carbonyl group is better stabilized than the fluoride. So this carbonyl group, okay, is better stabilized than the chloride because this carbon fluorine double bond, okay, is substantially stronger than carbon chlorine double bond. Although fluorine is more electronegative than chloride. Although, okay, so yeah, the electronegativity effect is overpowered by the size effect, overpowered. Okay, we actually have seen this in chapter 13, if anyone recall. If you recall the, we look at the halobenzene, their reactivity in electrophilic aromatic substitution, fluoride is actually more reactive than chloride. For the same reason, because fluoride can donate the lone pair to benzene ring better than the chloride. Okay? So the same argument, okay? So that is the reason why acyl chloride is the most reactive one. The size, the heteroatom size effect. That is the reason why acyl chloride, okay, is the most reactive type of carboxylic acid derivatives. Okay, because of acyl chloride, among the 4 official members of carboxylic acid derivatives, that's the only, the member where we have third period heteroatom bound to carbonyl carbon. Yes?
You said that carbonyl carbon is the most stable with the Cl?
No, it's the least stable with Cl. Because of the acyl chloride, okay, this is the only carboxylic acid derivative in which we have a third period element bound to the carbonyl carbon. All others, we have second period element. So carbon-chlorine bond, okay, is the longest bond we have, okay, longest bond. That means this bond, okay, is the weakest, okay. That makes this form makes the smallest contribution among all carboxylic acid derivatives. Yes, Andrew?
That's why it's most likely to react.
Yes, because of this form makes the smallest contribution, mainly because of the, chlorine is the largest heteroatom we have here. It's only a third period element, okay? So that makes this one, okay, acyl chloride most reactive. Okay? Although chlorine, as we know, is a bit less electronegative than oxygen. That we all know that, right? A bit less electronegative. But because of the sheer size, makes this carbon-chlorine bond, okay, really, really strong. So, really long, okay. So really weak compared to carbon-oxygen double bond or carbon-nitrogen double bond. So that the size effect of chlorine overpowers the electronegativity effect. Okay. Any questions? Yes.
So if we were to compare the reactivity of fluorine and chlorine attached to it, what would take priority, the size?
Still size. Yeah, so the acyl fluoride will be less reactive than acyl chloride. Still the size, okay? So in general, if the size plays a major role, size is the dominating factor here. Okay? So the chloride is the acyl chloride is most reactive one because of this the C carbon chlorine double bond is the longest, therefore is the weakest. Okay, so that makes this form makes smallest contribution. Okay. Now the next member, in the carboxylic acid derivative is acid anhydride. So acid anhydride features oxygen single bonded two carbonyl groups. Okay, so it can form this carbon-oxygen double bond, okay, which shows how well the carbonyl group stabilize. Okay, so because of oxygen is second period element, obviously carbon-oxygen double bond here is substantially shorter than the carbon-chlorine double bond here, stronger. Okay, so therefore the contribution of this form is sizably greater than the contribution of the stabilized form in acyl chloride. So that makes the carbonyl group in acid anhydride is sizably more stable than the acyl chloride. Therefore, it's less reactive. Okay. And I'm only showing here. I'm only showing the left side carbonyl stabilized, but there's no. Of course, just using the same way, you can see you can understand the right side carbonyl also can be stabilized by oxygen lone pair. Okay, so they are, basically the stabilization power of this oxygen lone pair bearing oxygen atom. Now, just pay attention to. Okay, if you look at this one, the stabilization power or electron donation power of this oxygen atom is shared, okay, by two carbonyl groups. Both of them want, right? Both of them want it. Okay, so as a result, each carbonyl only will get half of its stabilization ability. Half. Okay, so that makes the difference between the ester and anhydride, because in the ester you see, you still have the lone pair bearing oxygen atom can donate the carbonyl to donate the lone pair to its carbonyl. Okay, but the difference between ester and anhydride is in ester each carbonyl is exclusively served, stabilized by one oxygen atom. Okay, and in acid and anhydride, two carbonyl they have to share one electron donating oxygen atom. Okay, so each one only get a half. So that's why in ester the carbonyl is substantially better stabilized than anhydride, because of two people share one, two carbonyl share one electron donating oxygen, and in ester each carbonyl exclusively enjoy the stabilizing of a single oxygen. Of course, the ester is better stabilized. Okay. And the question between ester and anhydride. Now you look at amide. Amide I already explained earlier. The difference between amide and ester. Only major difference, not the only difference. Only major difference between ester and the amide, okay, is in the stabilized form, amide have the CN double bond, but in ester you have a CO double bond. So the difference between these two guys is it's easier for less electronegative nitrogen to donate its lone pair compared to oxygen, because as we know, nitrogen is sizable, not hugely sizable, less electronegative than oxygen. Therefore, nitrogen is more willing to give out its lone pair. So in amide, the contribution of this co-stabilized form is greater than the contribution of this stabilized form in ester, because nitrogen less electronegative is happier to give out its lone pair than oxygen does. Okay? So this form makes greater contribution in amide. When this form makes greater contribution, means carbonyl is better stabilized, less electrophilic in amide compared to ester. Any questions? So because of this in amide, this resonance makes this resonance form makes really greater contribution than the ester. So actually in amide, this CN bond has a significant double bond character. So if it has if CN is a pure CN double bond, we know just like CC double bond rotation is not possible, because if you rotate double bond, you have to break the pi component. Okay, and this has a significant double bond character. So the activation for rotation is actually really high, close to 80 kilojoule per mole, around 80 kilojoule per mole. Just to give you an idea, just what's the rotation energy barrier in a typical carbon-carbon single bond like acid? It's 12 kilojoule per mole. Okay, 12 kilojoule per mole, and this one 80 kilojoule per mole. So this really have a substantial double bond character. Okay. So this feature actually very important for the in proteins. Okay? In proteins, in proteins you have the proteins are amides. All proteins are amides. So the double bond the CN bond in protein is very difficult to rotate because of this reason. Okay? Very difficult to rotate. So you can see the CN bonding amide 135 picometers, and in the CN single bond 147, significantly shorter. Okay, it just shows that all CN bond has a very obvious double bond character. Okay, so this table, okay, I systematically explain, okay, why those carboxylic acid derivatives, okay, have the stability showing here. Okay, I hope you don't memorize instead of using the resonance form analysis I went through. Thoroughly digest why this carboxylic acid, derivatives have the stability, carbonyl stability sequence given here. Acid chloride, least stable, most reactive. Then the acid anhydride is just a bit more stable than the acid chloride, because the difference between here is CN double bond, CO double bond, and the carbon chlorine double bond. Okay, carbon chlorine double bond so much longer than CO double bond. So the chlorine cannot stabilize acid chloride to the same extent than oxygen atom. Then in acid anhydride ester, the difference is in acid anhydride, two carbonyl groups have to share one electron donating oxygen atom. In ester, this guy doesn't have to share. Okay, and then amide and the ester difference is nitrogen being less electronegative than the oxygen. Okay? If you understand the reason behind those carboxylic acid, why the carbonyl group stability is impacted by the structure, is basically how well the halogen, okay, not halogen, the heteroatom to donate its lone pair to the carbonyl carbon. That is a key reason. Okay, so the better the heteroatom can donate its lone pair, the carbonyl group will be more stable and less willing to react. Now let me ask you, if I have these two esters, both are esters, okay? Which one will have a more stable carbonyl? Left side one and the right side one. The key part is why. Which one which ester has a more stable carbonyl? Yes. Correct. Why?
Because C is less electronegative than calcium chloride, so it gives the electrons better than chloride.
C is less electronegative than F. That is perfectly correct. But if you look at these two esters, right? Here is the alkoxy group connect to the left side ester, okay? And the right side ester is this. So do you think you should compare electron activity of C and F, or you should compare something else? Huh? It's H and F. Okay. So, but the argument, I believe, the argument is correct because of the CH3 doesn't have a very strong electronic interaction with the O, okay? But the CF3, as we know in chapter 13 as earlier, okay? And also we saw it again in chapter 18. CF3 is a very powerful electron withdrawing group by inductive effect, okay? So that means the CF3 will still electron density away from the O, okay? That means the lone pair on the O will be less available to be given to the carbonyl group. Therefore, makes the right side molecule, the carbonyl group is less stable compared to the left side, because left side you don't have such an issue there. Okay. Now another example, let's say we can apply the same principle to answer the question. Okay. Now I have this CH2 and the CH3. Okay. And I have this one, O and CH. Which of those two esters, okay, has a more stable carbonyl? Top one, bottom one? Top one. So why the top one has a more stable carbonyl? Huh?
The top one is yes, the bottom one the bottom one is more acidic.
Huh?
The bottom one is more acidic, so it will pull the electron away from oxygen.
Very good. You can make two arguments here, okay? So this one is sp3. This one is sp2. So sp2, as we know, generally it's more electron withdrawing than sp3. So that makes oxygen lone pair less available. And the other argument we can make is the lone pair here, okay, can also be donated to the double bond. So that makes the lone pair, the oxygen lone pair less available to the the carbonyl carbon. Okay? So argument is the same. So if you have any clear pathway for the oxygen lone pair become less available, then that ester will become more reactive, because ester carbonyl, okay, its stability comes from the stabilization from oxygen lone pair. Okay, so if you have a structural factor takes the oxygen lone pair away for whatever reason, then the ester will become more reactive. Okay, so I'll just give you one example. The kind of esters considered among common esters is really reactive type of ester. So called p-nitrophenol ester is really reactive. Why? Because this ester, in this ester, the oxygen lone pair, okay, can go, look at it, come to here, come to here, come to here, and come to here. The ester lone pair can go all the way into a very electron-hungry nitro group. And for those of you who learn biochemistry, either the chemistry version of biochemistry, I believe, from what I heard from the student who took MCAT before, helped them tremendously in MCAT. Then all the biochemistry, but biology version, I don't know. I don't know what exact cover, but anyway, if you take the chemistry version, you're probably gonna see this type of compounds. Okay, so that is see because of the, as we know, nitro group is one of most electron-hungry group we have seen. Okay? It's more hungry than fluorine because fluorine, it has the ability to give lone pair back to the, pi system. But the nitro only can accept, electrons from the pi system. So that makes this ester one of the most reactive ester. One of, okay, yes.
The less stable it is in the reactive.
Yes, the when we look at the nucleophilic acid substitution reaction, the less stable the carbonyl is, the more reactive it will be. So here, if you look at this called p-nitrophenol ester, the oxygen lone pair can have very strong tendency to go into the nitro group. So it's very little left to stabilize the carbonyl group. Very little left. So that makes this kind of ester far more reactive than typical ester. It's actually the reactivity is only a bit lower than ester hydride. Okay, and the questions about the general principle for you to for you to assess the carbonyl group reactivity and the stability by looking at the structure. Mainly look at availability of the the phytoatom to stabilize the carbonyl group. Its size matters, and its the electronic environment matters. And the last example I want to give you in terms of carbonyl stability, okay, is this one. That's the last example, okay. So this guy, you think its reactivity is better than if you compared with, say, this one, ester, these two guys, okay? How you gonna let's say rank these three guys. How about their carbonyl stability? Just give you a hint, okay? Give you a hint before you answer, okay? So this compound is aromatic. Just this unit circled in the green is aromatic, okay? It's aromatic. It has 6 pi electrons, okay? So it's aromatic, okay? So how do we rank the carbonyl stability of those 3 compounds? Yes.
Since it's aromatic, it would be the most stable, so it would be the least reactive, right?
Think over. So out of those 3, let's say 1, 2, 3, which has the most stable carbonyl? 1, 2, and 3. Which one has the most stable carbonyl? Yes. No?
The aromatic ring is a lot of the electrons. So it's not.
See, think about it. Basically, the carbonyl, we are not talking about the entire compound stability, okay? We're talking about carbonyl stability. So carbonyl stability depends on the ability to be stabilized. Okay, yeah, Veronica?
Is 3 the most stable in this reactor?
That is correct, because 3, the nitrogen lone pair, is fully available. Actually, and see, both 2 and 3, the nitrogen and oxygen lone pair, those 2, they are fully available to stabilize carbonyl. It doesn't have other impact interfering with the ability. So both 3 and 2, they are reasonably stable. 3 being more stable than 2 because nitrogen lone pair is better at stabilizing carbonyl. And the key part is 1. Okay, how do we compare the 1 with 2 and 3? Huh? The key part is nitrogen lone pair available. There's a lone pair on the nitrogen. 1. Is the nitrogen lone pair available to stabilize carbonyl? No, because it's needed for the ring to be aromatic. So actually, the phosphor compound is highly reactive. It's actually highly reactive. It's comparable with anhydride. The exact reactivity I'm not asking you to memorize. Okay, but it's highly reactive compound because the nitrogen lone pair is not available because it's wanted by the ring to be aromatic. And the aromaticity provides a huge stabilization. So that stabilization is a dominating factor for the electron pair to go to the aromaticity side. Okay? So it will be very little is available to stabilize the carbonyl. Okay? So that's just how do you think about the key part is think about how well the lone pair is available to stabilize carbonyl. Okay? Because the lone pair is needed for the right side ring to be aromatic. So it's not very little left to the stabilize. Okay, let's have a break for 5 minutes. And if attendance